let's look at a few examples of surface area and notice how these integrals are a little different than arc length. So arc length, unless the function is really cooked up nicely, the integrals can get pretty messy. But with surface area, we have this extra piece out in front that often can help us with the integration. When we just were integrating ds for arc length, we didn't have this extra 2 pi r in front. So substitution was not a viable option typically. We had to have that perfect square trinomial business going. So let's notice what happens here when we have this extra factor. Let's see how it might come to help us. So we're going to simplify what's inside here, and we're going to distribute. So this x from the left square root is going to get moved in. Remember that if you have two square roots, you can combine the insides of the square roots and get the square root of the product. So that x is going to move to the inside, and let's simplify what's over here. We square the 4 and we square the root x. So we're going to end up with that. So this x goes in and we have 1 square root and we square the top and the bottom there. And now we can distribute that x across that expression. We're going to have square root of x times 1. And then x multiplied by 16 over x, the x's cancel, and we're left with just 16. That we can integrate directly. When we have a square root, we can do the power rule. We add 1 to the exponent. So the exponent becomes 3/2. And then we divide by 3/2, which means multiply by 2/3. Do we have to do a reverse chain rule here? What is the derivative of the inside here that would be used for substitution? What's the derivative? Derivative is 1. So we would divide by 1. So we're doing reverse chain rule, but there's really no effect because we're dividing by 1. So we don't have to put any division here. And then this is going to go from 9 to 20. We'll plug in our limits of integration. So we're going to have 32 pi divided by 3. And then this will be 20 plus 16, which is 36 to the 3/2 minus 25 to the 3/2. Those are perfect squares, so we can trigger the denominator here. Square root of 36 is 6. 6 cubed is 216. Square root of 25 is 5. 5 cubed is 125. And then we can do the subtraction there and get our final answer once we multiply those together. What is that, 91? So all we have to do is multiply the 91 times the 32, and we will get our answer. So what's that, 2,700 plus 2,912? Like that. Double check the arithmetic, but I think that's what it multiplies. Question?
Can you go over how you turn the ds into the square root and all that stuff?
So that's from arc length.
Yep.
And so anytime we have a ds, ds is going to be the square root of something with either a dx or a dy there, depending on the orientation. In this case, we're doing 1 plus the derivative squared. So that's what this is right here.
Okay.
So 2 pi r is the circumference, and then, well, actually, let me, 2 pi r, the whole thing in here is the circumference. So that's the circumference, and then ds is this part right here. So ds is always 1 plus the derivative squared underneath a square root. So we found our derivative here, and then we squared that.
Okay.
So that's how we got the the derivative is 4 divided by square root of x, and then we square it, add 1.
Right.
So ds is exactly arc length from the prior section. And then we have the circumference in front. So let's try another one. So here, again, we have 2 pi r. So we've got this function. It's going to rotate around the x-axis. It's going to create that funnel-looking object. We know that this ds up here, in order to convert that to a dx or a dy, we're going to take the derivative of this function, square it, add 1, and put it in the square root. So ds always becomes the square root of 1 plus y prime squared, possibly x prime squared if we were using dy instead of dx. So we're always going to start with the derivative of our function. So y prime will be 1/2. We bring down the exponent, we subtract 1, and then we multiply by the derivative of the base. Now if we simplify this a little bit, we're going to have 2 divided by the square root of 4x plus 6. So that's the derivative of the function. And if we square it, we'll have 4 divided by 4x plus 6. And then we'll add 1 to it and put it underneath the square root. So our capital S for surface area, or you could do SA if you prefer, it doesn't really matter. The x's are going from 0 to 5. And then the first part is 2 pi times the radius. When we look at our picture, the radius is this distance right here. Well, that distance is the function. So 2 pi times the function. So this radius up here is always going to turn into the function. So the function is the square root of 4x plus 6. So that's the circumference right there, 2 pi r. And then ds is always the square root of 1 plus the derivative squared. So we have 1 plus this expression. And this will be a dx. And once again, we have a product of square roots. And whenever we have a product of square roots, we can combine the square roots into 1 by multiplying the insides together. So we're going to take the inside of the left square root and multiply it by the inside of the right square root. And so what happens is that this 4x plus 6 gets multiplied by 1, and then it gets multiplied by that fraction. When it gets multiplied by 1, we get just 4x plus 6. When it gets multiplied by that fraction, there's a 4x plus 6 in the numerator, a 4x plus 6 in the denominator. So those cancel into a 1. 4x plus 6 over 4x plus 6 is 1. And we're left with just the plus 4. So it simplifies to that. This is going to give us another integral of a square root. And once again, we can integrate this directly. And because this is linear, we can use the reverse chain rule. Because that's a linear, it would be a linear substitution if you were going to use the substitution technique, which we don't have to do because it's linear. So we're going to take the 4x plus 10 to the 1/2. We're going to add 1 to the exponent. So 4x plus 10 to the 3/2. And I didn't leave space there for it, but we can put it out here, dividing by 3/2. So that's the power rule part. Add 1 to the exponent, divide by the new exponent, and then what's the last step? The reverse chain rule part. What's the derivative of 4x plus 10? 4. If it was chain rule, we would multiply by 4, but this is integration, so it's reverse chain rule, so we divide by 4, which is the same thing as multiplying by a fourth, or you could write it as division under this. It doesn't matter how you write it. So that will be our evaluation. So we will end up with 2 over 12, 4 over 12, so 1 over 3. The 4's are canceling. So we end up with pi over 3 here. So that's the combination of these constants. Now we plug in the 5, and we're going to get 30 to the 3/2. We subtract off the evaluation of the antiderivative at 0, so we're going to get 10 to the 3/2. Neither 10 nor 30 is a perfect square, so there's really not much you can do here. But most of the time, you're going to end up seeing the final answer written like this. 30 root 30 minus 10 root 10. And then you could factor out a 10 if you wanted. You could write it as 10 pi divided by 3. Factor out a 10, so we'd have 3 root 30 minus root 10. Would be our simplified final answer. And it's perfectly fine to leave it like this, but you're going to see in a lot of places that you can, fractional exponents are kind of undesirable. So if you can somehow get rid of those fractional exponents, which you can if the power is 3/2, then often it's written that way. Usually. Not always. This is totally fine up here on a test. This is totally acceptable. You can leave it like that. But if you can get rid of fractional exponents, it's usually a desirable thing. All right, let's see. So same idea. We've got a curve. We're going to rotate it around the x-axis. Tell me what, when you see this, so this function right here, we have to take its derivative. So spend a minute and take its derivative. Let's see if you can take the derivative right. Because if you don't take the derivative right, the rest of the problem's wrong. You have to be able to take basic derivatives. So write down the derivative there, and let's make sure that you see that derivative clearly. And this is a derivative that needs the chain rule, because it's got a base that has a non-1 derivative. So this method of derivative is called the power rule. You're bringing down the power, you're subtracting 1. And everybody sees that the power is 1/2 right now. Right? We think of the square root as a power of 1/2. So that half comes down, and then the base is 5x minus x squared. That stays the same. But then we subtract 1 from the exponent, 1/2 minus 1, negative 1/2. And then what is the chain rule? What are we going to multiply by?
5 minus 2x.
5 minus 2x. The derivative of that base is 5 minus 2x. So that's what's going to go here. Let's write this without any negative exponents. So this is going to be 5 minus 2x divided by 2 square root of 5x minus x squared. But then in all these DS problems, we have to square this amount. I find it easier to square it before we put it inside the square root. You don't have to, but if you find it a little bit cleaner to square it before you throw it into the square root. So there's y prime squared. So the surface area, capital S, is the integral. They give us limits of integration of 1 and 4. And then it's 2 pi times the radius. The radius is the function. The function measures this distance down to the x-axis. So it's 2 pi times the radius. So that is square root of 5x minus x squared. And then we multiply by the square root of 1 plus the derivative squared. So 1 plus the derivative squared, we already squared it, so we're just going to put this inside. And that's dx. And we're now in that same situation where we're multiplying two square roots. So if we have two square roots being multiplied together, the inside has to be distributed over to the inside. Well, the first part's easy. 5x minus x squared times 1 is 5x minus x squared. But then when it distributes to that second fraction, this 5x minus x squared is going to cancel with this 5x minus x squared that's sitting in the denominator. So that cancels, and we're going to be left with the numerator, which I'll FOIL out. So that numerator is 4x squared minus 20x plus 25. And the only thing left in the denominator is the 4. So we have that. So we FOIL the numerator. We divide everything by 4. And we can do a little simplification here, and we're going to notice that there's some cancellation. So when we're distributing that 4 goes into 4 once, so we get positive x squared. 4 goes into negative 20, negative 5 times, so we get negative 5x, and then plus 25 over 4. And we have a bunch of cancellation. These cancel, and the only thing left is the constant, 25/4, inside a square root. Square root of 25/4 is 5/2. So this is what it's going to simplify down to. That 5/2 can come out to the front. Square root of 25/4 is 5/2. 5/2 comes to the front. You multiply by 2 pi, the 2's cancel. And what is the integral from 1 to 4 of dx? 3. Upper minus lower. Whenever you integrate a differential, you're just finding the distance between these limits of integration. So this will be 5 pi multiplied by 3, which is 15 pi. So lots of basic algebra here from college algebra. Yep.
What does, like, when you have y1 and then parentheses 2, what does that mean? I don't understand.
Notation.
Yeah, and I don't understand what the step is there to go from, like,
So where am I looking? Y,
y1 to,
this?
yeah,
Y prime?
yeah,
The derivative.
okay,
So that's the prime notation for a derivative. So that says y prime, which is dy dx.
okay,
So you can always use prime notation, or you can use differential notation. And it depends on the context. Sometimes it's more useful to use differential notation, and sometimes it's more useful to use prime notation.
but what does it mean when we put it, like, a 2? Does
Up
it
here?
more- Yeah,
Square.
okay,
So that's squaring it. So if we look at y prime right here, once we do the chain rule to get y prime, then we're squaring it, which means, and if you have a fraction and you want to square a fraction, you have to square the top and the bottom. So when we square this, we take the numerator and we square it, which is putting a power of 2 on it. And then in the denominator, when we square it, 2 squared is 4. And if you square a square root, the square root goes away.
And are we just squaring it so we can plug it in?
So we can plug it into ds, because ds is 1 plus y prime squared.
Okay.
So the derivative of y gets squared so that you can convert the ds to a dx. So the formula for converting ds to dx is square root of 1 plus derivative squared. So we have to memorize that that's what ds is equal to. ds is always going to be the square root of 1 plus y prime squared. Yeah, so that piece we need to memorize. And that's what's going to replace that ds right there, that thing that I can't seem to put a circle around. Does that make sense?
Yeah.
Okay, so let's try another arc lengthy thing, or surface area thing. So the ones that we have just done were when our curve rotated around the x-axis. It's possible to rotate it around the y-axis. And here is a tip. When you're dealing with surface area, when the surface is built by rotation, if you're going around the x-axis, it's going to be easier to use a dx. When you're rotating around the y-axis, it's going to be easier to use a dy. It is possible, if you're really good at the shell method, where you have 2 directions happening simultaneously, it actually is possible to rotate around the y-axis and use a dx, and rotate around the x-axis and use a dy. It's possible. But in practice, it's just easier. If you're rotating around x for surface area, go with dx. Rotating around y, go with dy. It's just going to be easier. And if you look at the setup, there's your curve. You're going around y. You draw your radius. It's natural to think dy. dy is the thickness of this horizontal element that we're drawing. And like the one we just did, when we're rotating around the x-axis, your radial value is a vertical element, so it's easier to think of that as a dx. But you could get really, a little more complicated if you want. Now the big difference here is that your ds is going to end up with a dy on the outside, so instead of dy dx, also known as y prime, we are going to have dx dy, also known as x prime. So instead of a y prime, we have an x prime in there. So let's go ahead and figure out our derivative. Oh, it's horizontal, but this has been presented as a vertical function. Bless you. So what do we have to do if we want a horizontal function? We isolate x. Right, so anytime we have y isolated, we're measuring vertically. Anytime we have x isolated to the left, we're measuring horizontally. Since this is horizontal, I want to solve that for x. So x is going to equal, let's see, we multiply by 4, so we have 4y. And then we take the square root, and we get plus or minus the square root. So x is going to be the positive or the negative. Are the x values on this curve positive or negative?
Positive.
They're positive. We're in quadrant 1. So we're going to choose the positive square root, and we can make this 2 root y if we simplify it. So that is the function presented as measuring horizontal distances. That is the radius. That function is representing the radius. And now we have to take its derivative. So x prime, the derivative of x with respect to y. The half comes down. Half times 2 is 1, and then we get y to the negative 1/2, which we would write as 1 over root y. So that is the derivative. And then we have to square this derivative, so x prime squared. We square the 1 and we square the square root of y, and we get 1 over y as x prime squared. And so that is dx dy. X prime is dx dy, just like y prime is dy dx. So our surface area, capital S, we're going to have 2 pi times what? What is the radius here? 2 root y. So this x value is the function measured horizontally. So that x value is the radius. So that's what goes in here for r, 2 root y. And now we have to put in the ds. ds is the square root of 1 plus the derivative squared, so 1 divided by y, and then we have a dy. Limits of integration. Should they be y values or should they be x values? They should be, did I hear it back there? Y values, right? If we have a dy, limits of integration come from the y-axis. These were x values that were presented to us, so we don't want 2 to 4. We want to look at their corresponding y values, which are going to be 1 to 4. If you plug in x equals 2, you get y equals 1. If you plug in x equals 4, you get y equals 4. So we want to go 1 to 4. So those have to be y coordinates. And then once again, we have a product of square roots. When you have a product of square roots, you turn that into the square root of the products of the insides. So we need to take what's in this square root and distribute it to what's in the second square root. So we take the y on the left and we throw it into the inside. It's going to be y times 1. And then y times 1 over y. So we end up with that as our simplified integral. And we can integrate that directly. Add 1 to the exponent, divide by the new exponent. Those are any questions that you have going between these two? Everyone see that to get 2 square roots combined, you turn them into 1 and you multiply the insides. So that rule is the square root of a times the square root of b is the square root of a times b. The square, yeah?
Is it the same with division?
If you're taking the square root,
Yeah, if you have 2 square roots.
so if you have this, yes, it is the same. If you have the square root of a over the square root of b, you're going to combine them into 1, yes. So you get the square root of the quotient a over b. Exactly the same. And what is the derivative of y plus 1? So the derivative of y plus 1, this is linear. So when we do reverse chain rule, we always have to say, oh, what's the derivative of the linear expression? The derivative here is just 1. So when we do our division, you don't even see it. Dividing by 1 is invisible. So we're going to add 1 to this exponent, and that's where we get the 3 halves. So we add 1 to the exponent, get 3 halves, divide by 3 halves, and then technically divide by 1 because the derivative of y plus 1 is 1, but we don't have to write it. And then this is going to go from 1 to 4. So add 1 to the exponent, divide by the new exponent, and then divide by the derivative of the base. Derivative of that's 1, so we end up with this, which is 8 pi over 3. There are the constants. And then we plug in the 4 and we get 5 to the 3 halves. And then we plug in the 1 and we're going to get 2 to the 3 halves. And we subtract the 2. And you can leave it like that, that's totally fine. That would be acceptable on an exam for sure. But most of the time, this would be the preferred way to write it, where you turn your 3 halves power into a square root and you get rid of that fractional exponent. Any question on any step there? So that is the surface area of this surface of revolution. So we are jumping into 3 dimensions here for a little bit, but we're looking only at 3 dimensions where we have a lot of symmetry. So we can use some special math. We don't have to use Calc 3. No Calc 3, not yet. Okay, here's another one that's horizontal. So I want you all to take the derivative of that function up here. Here they've already isolated x, so it's measuring horizontal. So we don't have to convert and solve for x. So find that derivative. The biggest error I see is not taking the derivative right. If you don't take the derivative right, you're hosed for the whole problem. Chain rule. So chain rule says you have to multiply by the derivative of the base. The base of an exponential expression is, what's down below. So the base of this exponential expression is 12y minus y squared. So that half comes down, and the base stays the same, 12y minus y squared, but then we subtract 1 from the exponent, 1/2 minus 1. So that's the power rule part. Power down, subtract 1. But then the chain rule part says now you have to differentiate by the derivative of the base, which is 12 minus 2y. And if we simplify this a little bit, we're going to end up with, well, let's see. Do you see that this 2 is in the denominator, and in the numerator we have a 12 and a 2? We could divide the 2 out. So we can make that 6 minus y in the numerator. And in the denominator, we're going to have square root of 12y minus y squared. So that is our simplified x prime. And we know that we need to take that x prime and square it in order to convert the ds. So when we square x prime, the square of the numerator is 6 minus y squared. And the square of the denominator, well, if we square a square root goes away. So that's going to be our x prime squared. And now we can build capital S. Capital S is the integral. Our element is horizontal. The thickness of that is a dy. So we know that we want all y's inside that integrand. And the function acts like the radius. So 2 pi r. 2 pi r means that. It's 2 pi times the function. That's measuring, if you took this point right here and you rotated it around the y-axis, that's going to find the circumference at whatever y value you want. And then we multiply by ds, but ds is no good to us, so we have to do the conversion over to dx or dy, in this case to dy. So it's going to be 1 plus the derivative squared, which we did over here. I'm going to FOIL out the numerator because we're going to need to simplify this. So y squared minus 12y plus 36 divided by 12y minus y squared. So we have that. The y limits of integration are given to us, so we don't have to do any work to find them. we're told 2 to y, 2 to 10 on y. And now back to algebra. We take the inside of this square root, multiply it by the 1, take the inside of that square root and multiply it by this. And once again, we see this beautiful cancellation with the denominator on that second multiplication, which is going to be give us a lot of room for integration. So square root dy, 12y minus y squared multiplied by 1. So it's just itself. And then when we multiply it by the second fraction, it literally cancels out the denominator. So we have just the numerator, y squared minus 12y plus 36. Everything cancels but the 36. So these surface area integrals, you can see the cancellation from that outside function, the 2 pi r, can really make the integral a lot easier. Square root of 36 is 6. 6 times 2 is 12. So we end up with that. And the integral of dy from 2 to 10, 8. Integrating a differential gives you the length of the interval that you're integrating on. The length of this integral is 10 minus 2, 8. So this is going to be 96 pi. 8 times 12. Questions? The hardest part was taking the derivative and squaring it. That was the hardest part. That is often the hardest part. Okay, let's do one more. So this time we've got a dx situation. We always want to look at these types of problems, whether it's arc length or surface area, and decide dx or dy. What we always want to look at first, because that tells us how we're going to convert that ds. It's either going to be the square root of 1 plus x prime squared or the square root of 1 plus y prime squared. In this case, is it going to be 1 plus x prime squared or 1 plus y prime squared that goes in that square root? Y prime squared, because we have a dx. So if we have a dx, we're going to write the function as a y value and take its derivative. All right, so we've got a circle of radius 10, centered at the origin. We're looking at the upper portion of the circle of radius 10. So I isolated y, took the positive square root. The negative square root would give you the lower portion of that circle. So there's our function. The derivative, we use the chain rule. So the half comes down. We subtract 1 from that exponent. And the chain rule says we're going to multiply by, close, negative 2x. You did just say 2x, right? Yeah, negative 2x. So that negative right there is going to matter when we take the derivative. So negative 2x. The derivative of 100 is 0. That's a constant, so its derivative is 0. So the derivative there is negative 2x. The 2's are going to cancel, giving us x with a negative in front. So a negative x divided by the square root of 100 minus x squared. So there's y prime. With ds, we know that we're going to need a square. So I find it easier to find y prime squared out here instead of doing it all within the square root. It's a little simpler if we just square it out here. So you get that. Negative x squared is x squared. Square root squared is whatever's inside the square root. That gives us our y prime squared. So S will equal. Now, When we look at the shape that's going to be created coming around the x-axis, is there some symmetry we can use here?
Yes.
Definitely, right? We could start at 0 and go over to whatever that number is and then double it. The right half surface area and the left half surface area are going to match. All right, so let's do that. We're going to use a 2 for symmetry. So that's a 2 by symmetry. So we're thinking about going from 0 over to whatever that value is right there. Looks like 8. We'll have to figure it out for sure. Maybe they tell us, I can't remember. Let's see. They give it to us, so we're not even calculating anything. So we could go -8 to 8 with no 2, or we can go 0 to 8 with the 2. So that 2 out in front is doubling what's happening from 0 to 8. All right, so this is going to be the surface area. Let's see, our 2 pi times the radius. Radius is the function. So it's square root of 100 minus x squared. So there's 2 pi r. This is the circumference, 2 pi r, circumference. And then ds is going to be the square root of 1 plus y prime squared. Square root 1 plus, down there, y prime squared. That's x squared over 100 minus x squared dx. So all of this is ds. And now the inside here has to get multiplied by the 1, and then it has to get multiplied by the fraction. So the 100 minus x squared, the inside of the left root gets merged with the inside of the right root. And that's going to give us 4 pi integral 0 to 8. 1 big square root. 100 minus x squared times 1 is 100 minus x squared. And then when we multiply it by the second fraction, we see this common scenario where when this gets multiplied by the second fraction, or the fraction, I guess 1 is not really a fraction. So 100 minus x squared times this fraction, the numerator and denominator, those are canceling, and we just end up with plus x squared. So we have some more cancellation on the inside. Square root of 100 is 10. 10 comes to the front. 10 times 4 is 40. So we have 40 pi integral 0 to 8 of dx. And the integral of dx from 0 to 8, 8. So we're going to have 8 times 4, which is 32, and then a 0, and then a pi. So this is the surface area. 320 pi is the surface area. This is an application where we're painting this surface and we want a 1.5 millimeters of paint put on this surface area. Well, we need our units to match. This, we want this to be in meters, so 1.5 millimeters is 0.0015 meters. So they tell us that things are measured in meters. So this, if we are going to put the units in here, we're going to have a meters squared because that's surface area. And then if we want the volume of paint, we just multiply by 0.0015, and that will give us the cubic meters of paint. So the volume of paint will equal 0.0015 multiplied by 320 pi. And that's going to give us an approximation of something. I can't do that one in my head. So 320 multiplied by pi multiplied by 0.0015, 1.5 cubic meters of paint, approximately. So this one was an application where units were given. Anytime we are given units, we want to follow through with those units. So meters cubed for volume. All right, any step there that you want some clarification on using surface area? Finding surface area? So surface area, we're finding that it's a little easier than arc length because we have this extra piece in front of the square root. In general, when you're given an integral of a square root, you're hoping for a miracle because there's nothing out in front of the square root to absorb a substitution. So the fact that surface area puts a function out there gives us a lot of opportunity. That's a hard integral when it's just a square root, unless it's linear on the inside.
So for something to be on symmetry, does the function has to be, or like for example, a quadratic equation would have to be exact, or the parabola has to be exactly on the axis of the x or y?
It's possible to use symmetry when it's not, but that's primarily when we do. If you had a parabola that was, off over here, you still could use symmetry depending on what the problem was asking. It's possible. But usually what we're doing is thinking about the axes and thinking about whether there's symmetry with respect to the axis of rotation. And so that's usually the way we're using it. Now this, we're in 3 dimensions as opposed to this where we're in 2 dimensions. So if we were asked to find the area of this, we could do that and double it. But when we're dealing with a solid or a surface of revolution, then it's always with respect to the axis do we have symmetry. And so when we rotate this curve around the axis, we see that the right half and the left half have the same area. Yeah. So in math classes, teachers are always asked, why am I going to use this in the real world? What's this? Why is this important? Well, next chapter, physical applications. This is where you're going to use it in the real world. You're going to be an engineer. So this is the one section in the book where we really focus in a lot on applications. And many of the concepts you've heard of before, density, mass, volume, you've heard of these things. And many of you are in Physics 1 or you've taken algebra-based physics, and so these concepts should seem pretty familiar. Now, in the simplest context, to find mass, we just multiply density times volume. And density is a fishy one. You've got to be a little bit careful with density. Generally, when we think of density, we are thinking of a solid object, and we're thinking of a number of grams per cubic centimeter, or number of kilograms per cubic meter. Usually we're thinking solid object. But mathematically, we also can think of density of like a very thin plate and talk about grams per square centimeter or kilograms per square meter. You can think of 2-dimensional density. That is possible if the plate is super thin, like a thin metal sheet. You can also think of density 1-dimensionally. If you have a wire, you can talk about the grams per centimeter or the kilograms per meter. So we have to be a little bit aware when we see the word density, our instinct is to think solid object, centimeters per, or grams per cubic centimeter. That's our instinct. Oh, it's a solid. There should be a per cubic on the, we should have a cubic thing on the bottom. But that's not always the case. We just have to be aware of that. So in general, when there's not any variation in density, so the density is uniform, you can just multiply. If you know the density at one point and density is uniform, well, you just multiply density by volume and you're going to get mass. All right? That's not the interesting case. We are more interested in situations where the density is varying. Like you think about the Earth and you think about points within the Earth. The density is not constant throughout the Earth. The density varies. And so when the density is varying, then we have to use integration. So, I was in the process and it looks like I didn't finish. This box is supposed to be this box. I'm in the process of rewriting the notes so that the notes aren't pictures, So if you, like in OneNote, there is something called the reader, they call it, it's a screen reader. And if you hit play, it'll read the whole page. But a screen reader can't read pictures. So somehow I didn't finish this one. So this is just supposed to be that exact thing. So that this could be read by a screen reader. Point though, is that if the density is not uniform, if it's not a constant, we are going to use integration. And mass won't be just density times volume, it's going to be the integral of density. Okay? Now, here, notice that they've told us one-dimensional objects. So this is, when you look at that dx, you should be thinking units of length. And dx is a tiny unit of length. And so there's no cubic here, like the centimeters cubed. And if you look in here, it's going to be, you imagine the density, if you have a wire, you imagine the density on a small region of wire, and then you multiply it by dx, which is a small length of wire. So this is for the one-dimensional case. So if we integrate density, we will get mass. Now we'll just look at a couple of simple examples here where we have functions measuring density. So this is one-dimensional object, so it's one-dimensional density. It's grams per centimeter if we're using, or it could be kilograms per meter, whatever. So if that's a density function that's changing over the wire's length, we just integrate. If we integrate density, we will get to the mass. So mass is the integral of density. So if we want to find the mass of this wire, all we have to do is integrate the density function on that wire. And we will find the mass of the wire. Not too hard. So with these examples, we're just sort of understanding the real basics, that the basic concept is if you integrate density, you are going to get mass when you have variable density. So that's what the masses will be. We're just going to integrate and we'll get the mass. So this is not the case that we're going to spend much time on, but this is how you would do this. And they don't give us units here, but these would be, units of mass, if they gave us units. And then down here, just a quick reminder, how are we going to integrate that? What's going to be the antiderivative for 5e to the negative 2x with that linear exponent of negative 2x? What will the antiderivative be?
Negative 5e to the negative 2x.
Maybe you said it right. I think I heard some of the right things in there. So first we do itself,
Right.
and then we divide by negative 2. So divide by negative 2. So I heard you say a negative. So that is what it's going to end up being, which we could write as negative 5 halves. And then we could take this part right here as the antiderivative that we're going to plug the 0 and the 4 into. So we're going to have e to the negative 8 minus e to the 0, which is 1. So that would be our, and then units of mass. Kilograms or grams. Okay, so just basic concept in this section, with this one-dimensional density, integrate density, you get mass. That's the concept we want in our head right now. Integrate density to get mass. Okay, so the next basic concept is that of work. How much work is done by a motor, you, gravity? How much work is done in moving an object? Well, it takes a force to displace an object. And by definition, if that force is applied uniformly, then we can find the work done simply by measuring the displacement, multiplying it by the force. So in the simplest context, work is force times distance. So that's the simplest concept. So the simplest case when the force is constant. Just like the last one, where density could vary, and if density varied, we had to use an integral, and we couldn't just do the basic multiplication. Same idea here. If the force varies, you've got to use an integration to figure out the work. If that force is not constant, you can't just do the multiplication. But what you can do is the Riemann sum idea and break things down into little pieces where you think about, okay, well, the force on this little displacement is whatever, multiply it. Come over here, the force on this little piece of displacement is whatever, multiply it, and then add them all together. So you can use that concept of slicing and using a Riemann sum, taking a limit and getting a definite integral. So that's the Riemann sum. You take a bunch of little forces on those little distances, find the work done on each little piece, and then add all those little works to get the total work. Well, if we take an integral, if we take a limit of that as n goes to infinity, we get the work integral. So just like the last one, where density was varying, here force is varying. And if force is varying, you integrate force to get work. So work will always be the integral of force. Integrate force to get work. If the force is variable. If the force is constant, you can just multiply. You can just multiply the displacement times the force and you're fine. Or when you're in physics, a lot of times they give you the wagon problem. You're pulling the wagon, and so the handle of the wagon's at an angle. And so you find the component of force in the direction of motion, and you multiply it by that. That distance gets multiplied by the force. So if the force is in the direction of motion, then it's just pure multiplication. But if the force is a little bit tilted, you have to do they call it finding the components of the force vector, and you take the magnitude of the force in the direction of motion and multiply by the distance. But for us, the force is more complicated. It's varying point to point, so we have to integrate force to get work. It's going to be our key. All right, let's go ahead and take our break now, and then we'll do our first example of finding work from force on the next slide with a spring. And let's go, anyone that has questions on anything we did today or the homework, I will be here, and I can answer your questions during the next 10 minutes. Is the same example you'll see in a physics class. It's the simplest variable force problem there is. The simplest variable force problem there is the spring. And you all have experienced this. As you compress a spring, say 1 inch, takes a certain amount of force, but to depress it the next inch takes more force, right? It gets progressively more and more difficult to compress it another inch. Same thing with stretching it. So that's the concept. And the cool thing is that that change in force for a spring is linear, which is kind of shocking. Like as you're feeling it, it doesn't feel linear. It almost feels exponential. That the further you want to depress it, it feels like the amount of force is going up faster than just a linear function. But it's not. It's a simple function. The force function is simple, and this is why you always do this problem in physics and math first, because the force function is a linear function, which is so rare. That K is the spring constant, which is really similar. So the idea is that every spring has its own constant, which is giving you a sense of how stiff the spring is or how flimsy the spring is. It's similar to what you did in college algebra with those exponential decay problems. And every radioactive isotope has its own decay constant. Same idea. That decay constant in college algebra gave you a sense of the rate at which a radioactive substance decayed. Same idea here. The K value is giving us a sense of how difficult it is to compress the spring. So every spring's got its own decay, has its own spring constant. Every radioactive isotope has its own decay constant. So it's that same idea. So with the spring, we're thinking horizontal. We're not dealing with gravity. We're just thinking horizontal. And equilibrium, the front of the spring is at x equals 0. If we pull it to the right, we're stretching it. If we compress it, it's going to the left. So the S value, or the x coordinate over here would be positive. The x coordinate over here would be negative where the spring ends up. Okay. Big first step, just like in those college algebra problems, got to find K. We need to know what the spring constant is for a particular spring. So here is what they tell us. So part A, let's highlight the important things in here. That was a little small, let's make it bigger. So they tell us, they give us a data point. They say it's going to take a force of 15 newtons to stretch and hold the spring 0.25 meters from equilibrium position. So that's a data point that we can use to find K. So they tell us a force of 15 newtons, so that's the left side. We don't know K, but they tell us the displacement is going to be 1/4 of a meter. And that will tell us that this spring constant is 60. So that tells us that the force function for this spring is 60x. That is the force function. So if you want to displace the spring over an interval, then we're going to use that function. So this is part A, where we find the K value, build the spring function. B, how much work is required to compress the spring 0.2 from equilibrium? All right, so part B. We've got a variable function, variable force, so we have to use an integral. We're going to integrate our variable force function. And we're going to start at equilibrium. So it says from equilibrium, we want to compress it 0.2 meters. So should the upper limit of integration be positive or negative?
Negative.
Negative. Do we think it matters if you compress it 0.2 or stretch it 0.2?
Well, it matters in the answer.
It's not going to matter. It's going to be the same amount of work. If you want to compress a spring 0.2 or stretch a spring 0.2, it's going to be the same work. If we want it to match the physical situation, we definitely want to put in that, and I'm going to write that as a fraction. So that matches the physical situation. But it will be the exact same if you went here, because your linear function, when you integrate it, turns into a quadratic, which will absorb the minus sign. Let's watch. So if we do it over here, in either case, we're going to integrate and get 30x squared. And so whether we go from 0 to negative or 0 to positive 1/5, aren't those going to be the same? Yeah. And conceptually, you kind of know that. Whether you compress it or stretch it the same amount of distance, it's going to take the same work. So work's going to be positive. Plug in the 1/5. We're going to have 30 times 1 over 25 minus 0. So we're going to end up with 6/5 units of work. So we have meters, and the force is a Newton. So you can write this as 6/5 Newton meters, or what's the other unit of work? That takes joules. We can take away the Newton meter and write it as a joule, a Joule if you want. So either of those, totally fine. Joule, Newton meter, I don't care. Doesn't matter. Any questions on that idea? You're like, yeah, let's integrate linear functions. Let's do that all day. Integrating linear functions. Okay, now part C. How much additional work is required to stretch the spring 0.3 meters if it has already been stretched 0.25 meters from its equilibrium? So we're starting with it at 0.25. Let's write it as a fraction. Why do we write it as a fraction? Because a fraction is an exact value. A decimal, you have no idea whether it's exact or not. So we're going to assume that this is exact, write it as a fraction. So fraction 1/4, that's where we're starting. and we want to go an additional 0.3 meters. So we're going to go to 0.55, which we're going to write as 55/100ths, which we can, of course, simplify in a minute. So we're going from 0.25, and we're going to add that to get 0.55. So the work that we're finding is just the additional work. Function, 60x, dx. So we have the same antiderivative. We're going to go from 1/4 to, if we simplify that, 5 goes into there 11 times, 5 goes into there 20 times. So we have that. So 11/20 squared minus 1/4 squared. I'll do that arithmetic later, but that'll be our answer, and that will be, again, in joules. So springs, again, they're the simplest application. We're really just looking at these to get the concept that you integrate force to get work. We're going to focus more on some other ones. Spring is just an important gateway application. Gateway application. Here's the most complicated of these spring problems. So this is an interesting thing because, well, I'll show you. Describe it as I go. So calculate the work done to stretch the following springs. We're going to stretch them 0.4 from equilibrium. And in part A is going to be very similar to what we just noticed. So a spring requires, let's put Hooke's law up here, F equals kx. So we know we need to find k, and this first one is very traditional. It says it takes 50 newtons to stretch it 1/10 of a meter. So we have that, and we see that k equals 500 very easily. All right. So the force then is going to be the integral. We want to start from equilibrium, so we're starting at 0, and we're going to go to 1/10 of a meter, and we're going to integrate our function, which is going to be 500x. So we end up with this scenario, and we end up with 250 divided by 100. Plugging in 1/10 there, square the 10, get 100. Divide out, get rid of the 0, divide out of 5, we get 5/2 joules. So that is the common way, that's like the most gentle way to give you your data point to find k. They give you an f value, they give you an x value, you divide, you get your k. Now the second one.
They wanted us to go to 4.4 meters.
Oh, what did I go to? Oh, so 0.4 from their equilibrium. Where did I get one? Oh, I looked at it. Typo. 1/10, not 1/10. Not 1/10. What should that value be up there?
What? 2/5.
4/10 or 2/5. So that should be a 2/5 up there. And so that's going to be 250. And if we square that, we're going to get 4/25. So it looks like 40 joules. Does that look right? If we square that 4/25, 25 goes into there 10. That looks fine. Okay. Thank you. Part B. So look at this. This is not giving us an F and an X. This says a spring that requires 2 joules of work. Well, remember that work is going to be the integral of force. So it's telling us that we're going to get 2 joules of work, so left side of that integral, or left side of that equation. So 2 joules of work to be stretched 1/10 of a meter from its equilibrium. So 1/10 of a meter, that means we're going to start at equilibrium and we're going to go to 1/10. And we don't know the force function, right? We don't know the force function. Everyone agree with that? So in here, all we can do is write this as kx. We don't know what that k value is yet. The k value is unknown. So we take a general force function kx. If we integrate it from 0 to 1/10, it's being stretched, so physically it should be positive 1/10. That is what we have to solve to get k. Well, we can do this integration, right? This is kx squared over 2 from 0 to 1/10. 0 to 1/10. And actually, let's not do that. Let's come underneath. So this is going to be k divided by 2. And then 1/10 squared is 1/100th. And then we subtract off 0. Ah, there, k is all by itself, right? So here's how we can cancel it and get k. So k is going to be equal to, we multiply that, 200, so we get 400. So that's kind of an indirect way to get to k. The direct way is when they give you f and they give you x and you just plug and divide. But here they gave us an indirect way to get to k. And we still are trying to find the force to go from 0 to 2/5. It's just that we have a different spring now. This is going to be a 400x instead of a 500x. Do the integration and we get 200x squared from 0 to 2/5. So we're going to have 200 multiplied by 4/25. And 4/25. We can divide the 25 into 200 and get 8. And 8 times 4 is 32. 32 joules. So that's how the springs work. So Hooke's law, linear function. Anytime you integrate linear, you get quadratic. So that sort of does the symmetry thing for us. So on a test, if it says compressor stretch, it doesn't really matter. You know, I'm not going to mark you off if you use positive instead of negative, because the work's the same.
It wants the force though.
What's that?
It wants the force though.
Oh, if it wants the force is different. The force can be different, yeah. But there is the symmetry for. But in both cases, well, it doesn't matter. In either case, you're going to end up with the same exact work. So now let's get to the more interesting ones. So we have our basic concept that work is force times distance. So there's our basic concept. And when you're looking at an integral, you can focus on units if you want to make sure that you have the right integrand. Some of these problems can have crazy looking integrands, and the way you check that you're on track is that you have the right units in the integrand. So on the left we have work, which we know we're supposed to end up with Newton meters for work. And if you go through each one of these different factors, you should end up with Newton meters. If you don't, then you have the wrong, then something's missing. And I have a slide that I'm going to show you in a minute that talks about the units of each of these things in here. And we're going to talk about this in detail in a moment. Most of you, to memorize that formula would be kind of a headache. So what is usually the best thing with these applications is to come up with an acronym that's going to allow us to fill in the blanks and get to where we need to go. So the idea here, first off, is that we are now dealing with gravity. We're dealing with a tank, and we're going to be pumping water or something out of a tank, and that tank is sitting on the ground or sitting on a tower or whatever, but it's vertical and gravity matters. With the spring, horizontal, gravity is not going to matter. Gravity is insignificant. But here, when we have a vertical situation and we're dealing with force, we are going to use Newton's law, and the force is going to be mass times gravity. So now, with pumping problems, we're going to need gravity. So mass times gravity. Okay. So down here, there's this crazy integral with 5 different pieces. Let's talk about what each piece is, and then we'll look at the units in a minute, and we'll sort of talk about the concept. First is rho. Rho is density, and it's three-dimensional density. If we have a tank of water, three-dimensional density. G is gravity, 9.8 meters per second squared. A, cross-sectional area. If we've got some tank, A of y represents the cross-sectional area at y. Okay. D, distance. If we think about pumping, if we have a layer of water, a cross-section of water, and it needs to be pumped out of the top of the tank, so a pump is doing the work, that D represents how far that slice of water has to travel. Or if we were draining it out the bottom of the tank, D is representing the distance to the bottom of the tank where it's being drained, and that would be gravity doing the work. So with these pumping problems, if you have a pump, the pump's doing the work out the top, or if you just pull a plug, gravity's doing the work if it comes out the bottom. So in either case, D is distance traveled, and then dy is a y differential, so that has units of length, units of meters. So you're thinking about all these things. Distance has units of meters, dy has units of meters, a of y has units of meters squared, gravity, meters per second squared, and then density is mass per unit volume, so kilogram per meter cubed. And then you have a bunch of units that cancel. All right, so there's our crazy formula. If you want to remember it like that, that's totally fine. You know all the pieces. The Riemann sum idea, you find the work done in figuring out the work done for moving each slice of water, and then you add them all up, and then you take the limit of the Riemann sum, and you're going to end up with the integral. So the Riemann sum is breaking it into little works. Yep.
P is density?
Density,
Okay.
rho. Greek letter P, also known as rho, R-H-O. Yeah, that's density. So all the pieces are in there. Let's go to this slide. So here is where all the units are. So I've got all the units broken down for each of the pieces. In the second part of this section, we're going to be dealing with force instead of work. And we're going to have a slightly modified acronym. So here is the acronym that I want to focus on right now. Work is ADD volume. It's a very easy acronym to remember. ADD is a math word. And volume. So this is how we're going to find work. Here's how we're going to remember each of the pieces in that integral. ADD volume. And when we get to the next situation with force on a wall, ADD area. One thing I want you to just notice right here, how many dimensions of length are we getting rid of in going from here to here? If we go volume to area, we've gotten rid of how many units of length? Like volume is cubic meters, area is square meters, so we've gotten rid of one dimension of length. And isn't work force times distance? So if we take one more unit of length and multiply it by the force, we would get up to work. Okay, so we can think of it that way once we get to it. Now, these pumping problems, the easiest way to conceptualize them is with three-dimensional tanks. Yet the book does these one-dimensional things right out of the gate. I want to do those second. I'd rather go through the three-dimensional ones first because it gives you the best sense of how the formula works. And then we can look at, oh, well, when we have one-dimensional density instead of three-dimensional density, how does it change? Let's understand the three-dimensional version first. It will be easier. So let's come down here to cylinder, and then we'll come back to these one-dimensional density things in a moment. But let's do the cylinder first. This is the easiest to conceptualize. So, density of our liquid is constant. Water, the density is 1,000 kilograms per meter cubed. Gravity, when we're close to the surface of the Earth, is constant. 9.8 meters per second squared. We've got this cylindrical tank, 8 meters tall, 2 meters radius. It's filled with water. We want to pump the water right out of the top. So we're imagining that there's a way, whatever it is, there's a pump, and it's just going to be pumped right over the top somehow with this pump. All right? So here's how we start. We always are going to start with our acronym, WORK. So we've got to memorize this acronym, but this is going to make our lives so easy. And there's a reason I put volume in parentheses. We'll talk about why in a second. Talk about why. So here is the acronym. ADD volume. A, acceleration due to gravity, 9.8. So acceleration, 9.8. Density, and then distance. So acceleration, density, distance. So acceleration, 9.8. Density, oh, water, 1,000. Distance, okay, what do we mean by distance? We come over here, we look at a cross section, and we're pumping out the top. So this is the distance that is going to travel. We're going to think of this as the cross section at a height of y. So that cross section of water is a height of y. How far does it travel to get out the top? 8 minus y. If the whole tank is 8, and that cross section is at y units high, the distance up top is going to be the total distance, 8 minus the height of it, so it's 8 minus y. That is the distance traveled by the cross section at height y. There is ADD, acceleration, density, distance, ADD. Now volume, not the volume of the tank, not the volume of the tank. We are talking about the volume of the slice. So remember that a cross section is two-dimensional, it's got no thickness. As soon as we add thickness, now our cross-section turns into a slice. That slice has volume, and the thickness of that slice is dy. So the volume of the slice means, in this case, the area of the cross-section multiplied by the thickness, which is dy. So this is volume of slice. This has a constant radius of 2, so that's easier than a variable radius. So the area of that cross-section is, what's the area of that cross-section if this radius is 2? Pi r squared, so 4 pi. So 4 pi, that's area of cross-section, and then we multiply it by dy. So the 4y is area of cross-section. And then if you multiply by dy, all the stuff in green is volume of slice. So the dy is part of the volume. The dy adds the thickness. It creates 3 dimensions from the 2-dimensional cross-section. And then what do you think the limits of integration are? 0 to 8, because we have slices of water from 0 to 8. We want to add up. We want to accumulate the work done in moving each one of those slices of water out the top of the tank. So that's it. So if you can remember the acronym and understand that the parentheses, so it's sort of volume in quotes because it's not the volume of the tank, it's the volume of that thin slice. So the differential is always part of that volume. And then this all becomes fairly straightforward from here on. If you get the setup right, so that's going to pull out a 9800. The 4 pi is going to come out. And let's just simplify what's inside. Oh, it's just 8 minus y dy. So there is what we have to integrate. Once again, integrating a linear function. That's not bad. So I'm not going to do the math of multiplying this together yet, because maybe there's cancellation, who knows. So we integrate, we get 8y minus y squared divided by 2, 0 to 8. And that 0 is going to be 0. So we really just have to plug in the 8. Let's see if we have any cancellation. So we plug in the 8 and we get 64 minus 32, which is 32. We don't get any cancellation, so we just have to multiply that together. We'll do it exactly, so we'll leave the pi in there. So we're going to do 9,800 multiplied by 4 multiplied by 32. We're going to get a whole bunch of work. 125,4400 pi. So there, and this is joules. So I feel like doing these tanks helps build the concept better than the chain. We'll get to the chain in a moment.
The P equals 1,000.
Rho.
Sorry, the rho equals 1,000 kilograms over meters cubed per water. What
Yes.
does the rho represent?
So rho represents that, density of water.
Okay.
So whatever, if you're like pumping gasoline or you're pumping some other fluid, then you're gonna have a different density. In the math class, we usually always just use water, so it's always 1,000. But in a physics class, you would definitely be dealing with, gases or liquids that have different densities, and so that would change. Gravity, though, if we're on Earth, it's always going to be 9.8. If you're on the moon pumping liquid, it's going to be different. So rho always represents density of water for us. Density in general, but density of water for most of these applications. So now this one was particularly easy because each cross-section had the same area. If we have a different shaped tank, like the dreaded trough, we're going to have a different scenario here. Do you see that the cross sections are rectangles of varying area? Right? So if we draw let's draw the face of this trough over here. So if we have the face of the trough, and if we were to take a representative cross section, that's what the face of it's going to look like. So if we draw a representative cross section, that cross section then gets pulled, all the way back and across. Depending on the height of this, right, you're going to have different size rectangles. When you're closer to the bottom of that trough, you're going to have an area that's much smaller than if you're at the top of the trough. But important to see that the area is a rectangle, but it's changing depending on where that y value is. Okay, so that's what it's going to look like. Okay, so let's first get our formula down here. So our work is going to be the integral of ADD volume. Volume's in parentheses because it's not the volume of the tank, the volume of a slice. So when you form a slice, now you're imagining adding 3 dimensions to this, and the thickness of that slice is dy. So we're going to get the cross-sectional area, multiply it by dy to get a cross-sectional slice, to get a slice. All right, so let's fill in the blanks. We've got this beautiful acronym: acceleration, density, distance, ADD. Acceleration, density, distance. What do you think distance is going to be? So once again, they're saying we're going to pump it right out of the top. So that distance right there, this is a semicircle of radius 0.25. So 0.25 minus y. So 1/4 minus y. So this whole distance right there is 1/4. All right, so there's ADD. And now volume. All right, here's the hard part. So volume is going to be the cross-sectional area multiplied by dy. So this part right here is going to be the volume of slice. And then in here, we need area. So if we want the area of the cross section at Y, we need to know the width of this element and then multiply it by 3. So this is going to be 3 multiplied by the horizontal length of that red element. Okay, well, if we look carefully at this, let's draw it again over here. We are going to have to do a horizontal distance, so we're doing right minus left. So we need to come up with the equation of the right curve. So here is the right curve. Here is the left curve. So we have to find the equation of the circle, solve for x so that we can get an x value for the right and an x value for the left, and then take the difference. Okay, circle of rate. So I will always draw these sort of with reality in mind. So this is sitting on the ground or sitting on the x-axis. Sometimes people will always draw their horizontal line through the center of the circle, and then you have a shifted slice, which I find very confusing. I'd much rather shift the circle than shift the whole, than shift the ground. So this circle, it's x squared plus y minus the vertical shift equals the radius squared. So the radius is 1/4, so we square it. And this vertical shift, this center up here is 0, 1/4. Right, because the radius is 1/4, so that distance is 1/4. So this is going to be y minus 1/4 quantity squared. So there's the equation of the circle. And we need to isolate the x's. So let's come over here. We're going to have 1/16 minus, we're going to FOIL out this y expression. That's going to be y squared minus 1/2 y plus 1/16. Do you agree? The middle term, you do the negative 1/4 y, double it, and you get negative 1/2 y. Negative 1/4 squared is 1/16. So this x squared is equal to the 16ths cancel. So we end up with that. That's x squared. And then we've got to solve for x. And whenever we take a square root, we do plus or minus. So plus or minus. So that tells us that the positive square root is the right half. So the positive square root is the yellow, and the negative square root is the green. So if we want the length of W, we're going to do the positive square root minus the negative square root. Which turns out to be 2 multiplied by negative by this. Root minus minus root turns into root plus root, which is 2 roots. Which if you look at the picture, you could say, oh yeah, this distance right across there is the same as that distance, so it's actually 2 times whatever this distance to the right curve is. The distance to the right curve is this positive square root. So now we know the width of the element at y. And that's what we drop in right here. So this is the hardest one. This one where we have to find the width of a trough is the hardest. So 2 square root negative y to the 2 plus half y. And we're going right out the top, so it's 0 to 1/4. So let's see. We'll pull out the 98,000. We can pull out the 6. And then we have 0 to 1/4, and let's see if we get lucky in here. So here is our miserable looking integrand. The only real integration technique you have thus far is substitution. If substitution were going to work here, what would you choose for your u?
The inside of the square.
So say that once again.
Y squared.
It's got to be more than y squared. You're on the right track. You're looking inside here. But we want to let u be everything in the square root. So typically we're going to let u be whatever's in the square root, whatever's in the exponent, whatever's in the angle. Because right now the problem here is that you can't break that square root apart. Right? You can't take the square root of a plus b and make it the square root of a plus the square root of b. Freshman dream. Can't do it. So we always want to let u be whatever's the entire quantity in that root. So if we were to do that, when we take the derivative here, so this is only going to work if the derivative is present. And it almost is. Everyone agree on that derivative? If we look over here and we're like, out in front there's negative y plus 1/4. What if we factor out a 2 right here? If we factor out a 2, don't we get negative y plus 1/4? Right? If you factor out that 2, 2 times 1/4 is 1/2. So if we divide both sides of this by 2, we got it. And we can rearrange, the order doesn't matter with multiplication. The order doesn't matter with this here, right? We could write it as 1/4 minus y if we want it to match exactly. Commutative law of addition. So that's going to work perfectly. So we're going to have this 9,800 multiplied by 6, and then inside here we have square root of u, because we let u be everything inside that square root, and then this part, 1/4 minus y times dy, 1/4 minus y times dy, that's all going to turn into du over 2. And we'll put the over 2 on the front so that we can combine it with the other constants. Not too bad. Now, limits of integration. This is a pretty simple function to integrate with respect to u, so let's see if we can get u limits instead of going back to y limits. So when y is 0, there's y being 0 right down there. That's a y limit. When you plug it in here, you're going to get the corresponding u value. So if you plug in y equals 0 here, you get u equals 0. And now if we take the 1/4 y value and we plug it in there, maybe we need to write it down over here. We're plugging in 1/4, so we're going to have minus 1/4 squared, which is negative 1/16, plus 1/2 multiplied by 1/4, that's 1/8. So we have negative 1/16 plus 1/8, which is
Positive 116.
positive 1/16. An eighth is a 16th plus a 16th. So we're going to end up with a positive 16th. Okay, let's cancel out the 2 here. So we have 9,800 times 3 now. This will be u to the 3/2 divided by 3/2. And then this is going to go 0 up to 1/16. 0 does nothing. Plugging in the 0 gives 0, so we don't have to think about that. The 3's canceled. That's good. So we have 9,800 multiplied by 2, canceling these 3's. And then we have 1/16 raised to the 3/2 power. 16 is a perfect square, so we trigger the denominator first. Square root of 16 is 4, and then 4 cubed. So 4 cubed, we could do it lots of different ways. We could write it as 64. And then we just have to simplify this, so 9,800 divided by 32. And I can't think very clearly right now, so I'm just going to chop things in half a bunch. That's 4,900 chopped in half, and then chop in half again. And that's going to be 2, is that right? Oh my gosh, this is so dumb. This is so dumb. 1225 divided by 4. And that's as far as we can go. And that's joules. That's when you do, that's called tired arithmetic. Don't want to divide by 16. So the fast way would be to divide this by 16 and divide that by 16. Okay, so this is the hardest one. So we did the easiest one, which is the cylindrical tank. Now the hardest one is this trapezoidal trough. Now they ask us a couple of auxiliary questions here. If the length is doubled, is the work done doubled? So let's come in here and figure out where we put length. So come in here. There was the length right there.
Yes.
So if we double that, can't that 2 just factor all the way to the front and then give us twice what we just ended up with? Right? Yeah. If we double that, we're doubling the whole integral because that 2 could factor to the front. So this one is a yes for the part B there. If the radius is doubled, is the required work doubled? If the radius is doubled. So if that radius is doubled from 1/4 to 1/2, then we're going to have a trough face that's, oh, I called that a trapezoidal. Why did I call it a trapezoidal trough? That's semicircular trough. If we double the radius in this semicircular trough, if we double the radius, do you think that doubles the work? Now if we look at where the radius is in here, the radius came from, let's see, what the radius we had to, down here we had to use that radius to build the equation of this circle. And that equation is going to be dramatically different. It's not just a multiplication of 2 out in front. So this is going to be a no. When we double the radius of this circle, the problem's dramatically different. But it's not different in a constant multiplicative way. All right, so we've done the hardest one, we've done the easiest 3-dimensional one. Let's do one that's middle of the road. An ice cream cone. So this one, middle of the road. Although, let me ask you one random question. With the cylindrical tank, if you pump the water out the top, a pump is doing the work. If you just pull the plug and let it drain out the bottom, gravity's doing the work. Would those be equal? The work done by the pump or the work done by gravity? For the cylindrical tank. The answer is going to be yes, because each cross section is the same, and there's going to be just as many cross sections going in one direction as the other with equal area. The top cross section has the same area as the bottom cross section, and if you go different directions, you'll have all the same cross sections overall. If you take this cone, we don't have that vertical symmetry. If the pump is doing the work or gravity is doing the work, you will get different answers. Which one's going to do more work, the pump or gravity here? So gravity is going to be coming out the bottom, pump's pumping out the top. What
The pump.
do you think the pump's going to do bigger work?
Well, it's working against gravity.
Well, but if we look at the magnitude of the work,
Oh, well, then that.
So think about it this way. The biggest cross-section is up here at the top. So the work done in moving it all the way through the bottom, that biggest cross-section has to travel the furthest if gravity's pulling it down. Whereas the pump, the biggest cross-section is going very close to where the exit point is. So gravity is actually going to do more work. There's more work that's going to be done. Whether it's gravity or the pump really doesn't matter. If we pump it out the bottom, more work is going to be done by moving the water through the bottom than moving the water out the top. And so if you can do the calculation, and I'll show you where the one difference is. We'll get to it in a minute. Well, let me just ask you. If you take your cross section right here at a height of y, how far does it have to travel if it's going outside the top?
6 minus y.
6 minus y. How far does it travel if it goes out the bottom?
Y minus 6.
Just y.
Yeah.
Because that y is measuring the height you are above the vertex of the cone. So if you're 1 meter above the vertex, that cross section there is going to travel 1 unit. So the smaller slices are traveling a smaller distance for the pump, for the draining out the bottom. The smaller cross sections are going to travel further for the pump. Right? But the bigger ones are traveling closer for the pump and further for gravity. So this distance right here is y. So when we get to the distance in ADD, distance, that's going to be for the pump out the top. That would be for the draining out the bottom. And so you can just change that one piece in the integrand and then figure and see the difference in the total values. All right, so let's set up our acronym. So work is ADD volume. So ADD volume. And again, the volume's in parentheses to help give you a mental clue that it's not the volume of the cone. Right? We're going to take a slice in here that has a thickness of dy, and it's the volume of that slice. It's not the volume of the whole cone. All right, this is going to be an integral 0 to 6. Acceleration is 9.8. Density of water is 1,000. So instantly we know A and D always when we're dealing with water and gravity. And you already told me the distance that the cross section at a height of y travels is 6 minus y. You already told me that. So there is ADD. Now we need the volume of the cross section, the volume of the slice more correctly, the volume of the slice. So we need to know the radius. This cone has varying radii, depending on where you draw your cross section. So what we need is this function that represents the right edge of the cone, and we need to solve that for an x to measure horizontal distance. If you envision your coordinate system right there, isn't that just a line through the origin? The equation of a line, mx plus b, if that line is going through the origin, mx plus 0. So it's just slope times x. And the slope, so this line right there, y equals, let's see, slope is going to be the y over the x. Yeah? Up 6 over 1.5. How many 1.5s go into 6? 4. So that is the equation of that line presented as a y value. So measuring height, we want to measure distance sideways. So we divide by 4. So that is the radius of the cross section at a height of y. If you plug in y equals 0, the radius is 0. If you plug in 6, you get a radius of 3 halves, 1.5. So that is our radius. So now we come over to build our important stuff here. So this is going to be area in there, and then this is volume. So the area, all the cross sections are circles. Pi r squared. So pi times r squared. And once again, if you were doing the draining out the bottom, the only thing that changes instead of 6 minus y, you would just put a y. And that will tell you draining out the bottom. So this is going to give us a whole bunch of constants to the front. Let's get our 98,000, which we keep seeing. Or 9,800. 9,800. Or did I do it wrong?
What's
Let's see.
9,800?
No, it's 9,800. 9,800. All of a sudden the decimals and the zeros are looking like soup. All right, so what else can come out front? A pi can come out front, and a 16 in the denominator can come out front. We're getting 0 to 6. We have a 6 minus y, and we have a y squared. I think I pulled out all the constants. The pi, 16, yeah, that looks good. And let's just leave the constants out here alone for a moment, because maybe we're going to get some other constants coming from this integration. So 0 to 6, we have to just FOIL this, or whatever it's called, distribute it. So we have that. And then we're going to integrate it, plug in 0, plug in 6. I'll do the arithmetic once class is over. You know how to do that. That's polynomial integral. But that's the concept, though. The most important thing is this setup. Is there any piece of this setup that is nagging at you that you're not sure about? So ADD volume. And I'll finish off this integral piece. I want to now talk about the one-dimensional case. So let's go back to this one-dimensional case right here. So we know our ADD volume thing, and when we are dealing with a one-dimensional density problem, instead of dealing with volume, we deal with one dimension, we're dealing with length. So our clever little acronym, if we ditch 2 dimensions of length, it's going to become ADD length instead of ADD volume. We get rid of 2 dimensions and go from volume down to length. So they try to trick us here. They tell us that our climbing rope's a standard 60-meter rope, right there. And they give us a 9.4 millimeter diameter rope. If we are dealing with one dimension, does the diameter of the rope matter? No. That does not matter. That is extraneous. How do we know that this is one-dimensional instead of 3-dimensional? Well, if you look at this density function, they give it as grams per meter, not grams per meter cubed. If they gave us a density function that was grams per meter cubed, then, oh yeah, then we need to do the ADD volume because they've given us a density that's measuring a volume density, not a length density. So that's how we know right there. Not 3 dimensions. So our acronym becomes this. This whole parenthetical part is just dy. Right? There's no area. We don't put in an area. So normally we do area multiplied by dy. We're just ditching the area, so it's just a dy. So this becomes integral. We're dealing with 60 meters, so 0 to 60. And it's hanging freely from a ledge, 60 meters. How much work is done in pulling the whole rope up? So we've got our cliff. We've got our rope hanging off the cliff, 60 meters, and we just want to figure out the work it takes to pull the whole rope up. Okay, so this is going to be I'm going to do the cross section at Y. So it's just like a link of rope. If you imagine it as a chain, you can think of it as a little link or whatever, a little tiny piece of rope right there at Y. How far does that tiny piece of rope travel?
60 minus y.
60 minus y. So let's go. A, gravity is still 9.8. Density, 55 grams per meter We don't want grams, we want kilograms.
So it'll be 1,000.
So there's 1,000 grams in the bottom, 1,000 grams for 1 kilogram.
That's a nice repeat.
So it looks like that. And then distance traveled for each segment of rope, 60 minus y. And now our parenthetical part, oh, it's only length, so it's just dy. Now the rope is very symmetric, like the volume of that cylindrical tank. If the question said how much work is done by gravity if we just drop the rope, what's the only thing that changes in here?
Y.
This would just be y instead of 60 minus y. If you replace this 60 minus y with just y, you will get the exact same answer. You could do that. All right, so now we're just going to pull all the constants to the front. We've got the 9.8, we've got the 55 over 1,000. Integrating 0 to 60. Actually, we can do the integration. We're going to get 60y minus y squared by 2 divided by 2. 0 to 60. The 0 is not going to contribute. So we just have to plug in the 60. I'll do that right after class. Do the arithmetic part. So the setup part, is there any piece of this ADD length that you're not sure about? Yeah?
So when we say 60 minus y, are we saying we're basically counting bottom to top or top to bottom?
So this is going, so the y's, these are representing going from the bottom to the top. And if we're down here at 0, the 60 minus y is going to give us 60. So this piece of rope is going to travel 60. If we take that piece right there, it's going to travel 30. If we take that piece right there, it's going to travel 10. So this represents the total traveling of each piece of rope. So when you're at the bottom, 60 minus y, that piece is going to travel 60. And so when you imagine dropping the rope, it's just reversed. The top piece is traveling 60, the bottom piece is traveling 0, and it's gravity that's pulling it down instead of you yanking it up. Does that make sense? So instead of you doing the work pulling it to the top, if you just let go of the rope, same amount of work is done, it's just done by gravity. Which is why we like, when we're building things, to use gravity whenever we can, because it's free work. Right? So I want to talk about, we'll do this chain problem on Thursday. I want to talk about this for 1 second. Because this is super interesting. So we've got a 40-meter chain with density kilogram per meter. All right. This chain is going to be pumped, is going to be lifted halfway up. And there's 2 ways to do this problem. I distinguish the 2. One's called, I call the reality method, and one's called the initial state versus final state. So if we're not pulling the rope all the way up or the chain all the way up, we're not dropping it all the way to the ground, we're just lowering half of it kind of thing. So we're not doing the whole rope. This is interesting. So these dots up here are, these orange ones are representing the physical links of chain that are going to be cranked up to the top. So here is the initial state of the long chain hanging, and when you roll it up 20 meters, it's going to look like that. These links are just hanging. So these links are hanging, and then you pull up half of the chain, those links are still hanging. So that's what it looks like in reality. You could imagine these lower links as a block. And so this is another way to think about this reality method. You can just treat, if you're just lifting that bottom chunk of links, it's just like lifting a block. And that is the simplest work. Work is force times distance. And when we do a block, all you have to do is multiply the mass times the distance, and you're going to get the work done. So you could, this would be the reality method where we're going to crank from links at height 20 to links at height 40. Those are getting coiled up, but then this black chunk is really just a block being lifted. So we just have to do the force times distance here, MGH, force times distance. Okay, so then I had a physics student a number of years ago who said, well, why can't I just integrate from 0 to 20 and I get the same exact answer? I was like, I don't know. I'm a math teacher. I do it based on the reality. And this is the reality, that you're winding up from 20 to 40 and then you're adding this bottom section as a block. Well, then I started doing problems and investigating, talked to a friend of mine who's got a degree in physics. And what this method shows is, I was calling it the initial versus final state method. And so what you could envision is that, okay, we've got these 20 links that are hanging, and in the end you end up with 20 meters of links hanging anyway. You could imagine some alternative universe where you just took the bottom 20 meters of rope and lifted it up to the top, or chain, and left the top half hanging. So there's the initial state, there's the terminal state, but you could imagine just lifting these ones, and you get the same exact answer. You could go 0 to 20, lift those all the way up, and then your distance formula, your distance factor is still going to be 40 minus y. It's just that your y's are going to be down in here between 0 and 20. And so I did the math down here, and you will end up with the exact same value. So it's just sort of interesting. Physics people tend to be more inclined to do this. Math people tend to be more inclined to do that, but it's interesting to look at the differences between the two and see that it doesn't really matter. But you could imagine the lower chunk of links being magically flown to the top. That's the final state, is that 20 meters of chains are up the top. So both will work. All right, let's stop there. If you have questions, I will stick around as long as you need me to stick around. Otherwise, I will see you on Thursday.